would be William Pearson. He will tell us about galaxy merger identification of big data. So,
yeah, so I'm William Pearson, and I want to kind of discuss how we can identify galaxy mergers with the huge amounts of data that we're going to come up with in the next few years with things like LSST and Euclid coming online. So I should probably explain why I think at least mergers are interesting, despite the fact that they're quite nice to look at. They form a fundamental part of how we understand the universe works. So, Lambda CDM cosmology predicts that more or less all galaxies at some point in their history will find a friend and smash into each other. The results of this is you get morphological transformations. So your disk galaxies, for example, can turn into ellipticals. The tidal forces involved with these interactions can also move dust and gas around inside the galaxy. So it can force material into the center of the galaxy, and you can feed the AGN, the supermassive black holes that Artem has been discussing. The same forces can also compress gas and increase the star formation rate, or it can disperse the gas and reduce the star formation rate of the galaxies. They're also interesting if you're an infrared astronomer. The brightest infrared galaxies are typically found to be merging galaxies. And then this links in with the star formation rates. And the idea is that, at least for some mergers, you get massive star formation rates in these galaxies. You get starbursts. So if we want to study them, we need to find them. There are a number of different ways that people can do this. There's the Clothespin Method. So you take your galaxies in the sky, you take spectroscopic redshifts, you find ones that are close in redshift and close on the sky, and then these are probably interacting in some capacity. The issue with this is that it's an expensive thing to do. I doubt anyone will ever get an all-sky spectroscopic redshift survey with high-quality redshifts. It's unfortunate, but it's just the way things are going to go. So there are also other methods we can use. You can use morphological statistics, so things like concentration, asymmetry, smoothness, Gini, M20, Cersei index, whichever ones are your favorite. These are relatively easy to obtain. There are lots of codes out there that will do this for you relatively quickly. The problem is making merger selections with these statistics are not always reliable. So for example, I've done work before with looking at Gini and M20, and the cuts that are traditionally used in literature, you can get quite high contamination rates of things that you think should be mergers that aren't mergers. And it also relies on high quality observation data. You need reasonable resolution to be able to accurately determine these statistics. And then, of course, there's the good old human eyeball. We're quite good at doing this kind of thing, but the issue then lies in that I can do it today and say, this is some result. Someone else can do it tomorrow and they say it's some other result. And then I can do it the day after again and come up with a different result again. So they're quite hard to reproduce. And they're not easily scalable. Galaxy Zoo does a reasonably good job of this. But even they admit, with the huge data quantities that we're coming up with in the next few years, they aren't able to keep up with the amount of data that we're going to get. So we need some other method. The method that I've been looking into is deep learning, and I thought I should at least give people a vague idea of what this means. You've probably heard of the term before, but what it boils down to when you get rid of all the jargon that people put around this, it's just a series of matrix multiplications. So in this short little equation that I've put up in front of you, my mouse won't appear. There we go. X is the input into what has been dubbed a neuron. So this is a vector from however many other neurons you have below you. You multiply these by some weight values. The weights are what are learnt. You add a bias value, which is also learnt, And then in this example, you then pass on the highest of 0 on this, the sum of this equation. The complexity and why it's only really picked up as an idea recently, despite being kind of introduced in the 80s, if not before, is you need to do this a lot to be able to get any decent sized results. So we're looking at galaxy mergers. Let's say we want to reproduce the human visual classification. We need something to do with images. These are typically done with what are known as convolutional neural networks. This comes up as CNN and ConfNet in the literature. And they work quite simply. You have some image you'd like to classify. You have a small, typically square size of a few to a few tens of neurons by a few to a few tens of neurons. So let's say 5 by 5 for simplicity. You convolve with the image underneath this square, hence convolutional neural networks. You step this square along, if you like, left to right, up and down your image. This helps to reduce the number of neurons in your network and hence reduce the number of parameters you need to train from, because networks very quickly get to millions and millions of trainable parameters. All our maths happens, and then if you train your network correctly, this image that you see in front of you isn't a galaxy merger, it's something else. But at the same time, if you pass it in a galaxy merger, assuming everything's been done correctly, you'll correctly identify that we have a galaxy merger in front of us. So this is a kind of complicated, fairly, well, reasonably new technique. So why are we doing this instead of something else? The main advantage is speed. So with the Vieira-Rubin Observatory Euclid, they're expecting to observe billions of galaxies. So for argument's sake, let's say we have 1 billion galaxies we'd like to classify. If I sat down, maybe if I'm lucky, I can do one every 2 seconds. So that's 30 a minute. So that's over 500,000 hours I would have to sit there and do it. And if I did nothing but classify galaxies non-stop, not sleeping, not eating, it would take the next 63 years for me to get through all of, so let's say, Euclid's galaxies. I'm fairly sure that you'd agree this isn't really a tenable idea. And deep learning for the network that I'll show in a few moments, we can do about 475 per minute. So it's a factor of 15 faster. And then this is 35,000 GPU hours to do all of Euclid or all of LSSD, which is about 4 years non-stop. And this is more easily scalable as well. So this is just on one GPU. Let's say I have 2, that's 2 years instead of 4. And I think you'd agree that 1 GPU hour is significantly cheaper than a man hour. So it's a cost-saving measure and it's a time-saving measure quite considerably. So if I want to look for mergers, I need to have some data to play with. And I want to play with the data in NEP because it's quite nice. So I need a network to be able to do this. I do it in a kind of hybrid type method, I guess you could describe it as. I have a traditional convolutional neural network where I feed it single R-band images of galaxies that I know are mergers and galaxies I know are not mergers. I also combine this with a more traditional deep neural network using the morphological statistics that I mentioned before, so things like concentration, asymmetry, smoothness. I then combine these two subnetworks with another kind of neural network on top of them, and then eventually we end up with these classifications where you have a kind of what can be considered a probability that a galaxy is a merger and a probability a galaxy is a non-merger. So to do training, we need training data. I'm doing a class balanced approach. So I have just under 3,400 galaxies. These comes from the kids' gamma data. The mergers have been examined by people from Galaxy Zoo. And then there's further selections using the smoothness and asymmetry parameters. I have just over 1,500 mergers, and then I pick 1,500 non-mergers. And all of these are at redshift less than 0.15. So if we follow on from the discussion Artem was having about what parameter space can you really probe, this is for redshifts that are relatively low. The Hyper SupremeGAM strategic survey program has R-band data, which is comparable to the HSC data in NEP. So we make cutouts of these and we derive their morphological statistics. How well does this do? We have various statistics. So recall, this is the fraction of galaxies that are, fraction of mergers, sorry. Fractions of mergers that are correctly identified, and the specificity is the fraction of non-mergers that are correctly identified. So we have 91% for our recall, 84% for specificity. And the accuracy, in this case, this is class balance accuracy of 87%, which will be artificially inflated if you have imbalanced classifications. And we apply this to the NEP data from HSC using the catalog that was discussed earlier. This gives us just over 2,000 galaxies that we can have a look at that meet our redshift criteria, of which we find 400 or so mergers and the rest are non-mergers, which gives us a fraction of about 20%. And I have, there we go. We know these are wrong. Well, we know some of them could be wrong. So the best way to do it with one of the advantages of NEP is, as it's a relatively small field with high quality data, it's feasible to check things to make sure we're getting what we think. So Luis, a PhD student here that I've been working with, has currently looked through about 380 of our mergers. He finds that 201 of those 380 are actually mergers. If you scale this up to the full merger sample, it's about 237. And we also get false positives, so non-mergers that look like mergers. In this case, it's 179, or if you scale it up, 211. And the things like the image you can see in front of you, the two galaxies in the center, the red one and the blue one, are the ones that are being identified by the network as mergers. But if you look at them, they're probably almost certainly not actually involved with each other. So this gives us a merger fraction of about 12%, which is surprisingly higher than what we expect. You can do some sums based on the statistics of the network, and the network expects that we have actually 167 mergers, which is about a fraction of 8.3% merger fraction. So the network is doing better than it thinks it is in detecting mergers. So we want to do some science with our mergers. So this is some ongoing work that I'm doing, looking at merger fractions in clusters at the moment, with the idea of, does the environment influence our merger fraction? I'm using a different catalog for this than the HSC band merge catalog. There is ongoing work in the NEP group looking to create a cluster catalog at redshift of less than 0.15. Unfortunately, this is just one cluster with 26 galaxies. And there's another nearly 7,000 galaxies that aren't inside a cluster at this redshift. When you do our classifications, this is just the network classification, so we've not gone back and checked it. 19% of cluster galaxies are mergers, which is 5 out of 26, and 21% of field galaxies are mergers. Because of the relatively low number of cluster galaxies we have to play with at the moment, it seems to suggest that if you're in a cluster, if you're outside of a cluster, the galaxy, as far as mergers are concerned, doesn't really care if it's within or without these kinds of environments. So I will summarize. We've made a neural network which shows speed advantages. NEP's a great place to test this. Our neural network's doing better than it thinks it is, but there's ways to improve. early results suggest that clusters don't really influence the merger fraction. We want to push this to higher redshifts, which will give us more clusters and more statistics. And there's ongoing work by Luis to clean the merger sample. And I will leave it there as I think I've run out of time. Thanks.
Thank you very much. Questions and comments? We start with Yatin. What's the typical dispersion of the NEP clusters?
Sorry, I didn't hear. Can you repeat?
Question is, what's the typical dispersion of the NEP clusters?
I haven't looked. You would need to talk with Kevin. He's the one who's done the cluster catalog.
Kevin, are you here?
Yes.
Any idea?
Probably I'm the right person to answer these questions. So the velocity dispersion, we haven't calculated about that because we don't have, I will have to say the result we have is just preliminary. And to calculate the velocity dispersion, we need the spectroscopy. Yeah, so I haven't calculated yet.
My actual question is, why is the difference between the field and cluster so small?
So Yatin is asking why the difference between field and cluster is so small.
And because mergers do not easily happen in high velocity dispersion environments. So
Because merger doesn't happen easily in high velocity dispersion like cluster.
Yeah, so the answer is I don't know. I was expecting going into this that our merger fraction would be lower based on some other work I've done with group galaxies that I wasn't presenting here. As your group becomes larger, your merger fraction drops, which I think agrees with what you're saying, that the higher velocity dispersion environments have fewer mergers. Why we don't see that in the clusters, I think partially is we're only looking at 26 cluster galaxies at the moment. So I don't think we have enough to accurately or reliably say that the merger fraction is higher or is lower. I mean, this is very preliminary stuff at the moment.
Okay. The next question is by Nelson. How do you judge neural network is doing better than human?
That's the big question. I don't think it is doing better than a human at the moment. I mean, so if you take the example of the work Luis has been doing by visually identifying and going back and checking some other data as well, there are about half of the mergers that we've identified with the neural network aren't actually mergers. So humans are, at least with this network, humans are still better, but we are unfortunately slower than our robotic counterparts.
Well, I can imagine like taking small sample and then check it by eye and then see which one is producing more reasonable results.
Yeah, so that's what Luis has been doing.
Okay, so now the time is up. So thank you, William. We need to move on.